Welcome everybody to this webinar. So to mark its 20th anniversary, Climate of the Past, an interactive journal of EGU is launching a special webinar series celebrating 2 decades of leading paleoclimate science. So each webinar will emphasize the journal's scientific diversity and impact, featuring 2 invited talks of 25 to 30 minutes from leading researchers across different areas of paleoclimate science. Talks will be followed by a live 30 minutes Q&A session, allowing for discussion and engagement with the audience. So by the way, my name is Denis Didier Rousseau, and I am one of the co-editor-in-chief of Climate of the Past and co-founder. So now I leave the floor to my co-convener, Martin Clausen.
Yeah, thanks a lot, Dennis. My name is Martin Clausen. I'm a meteorologist by training and now retired, or let's say, well, do what I want to do now, a lot of research. Yeah, I was also one of the old co-founders, but I'm still on the editorial board. Yeah, now today we will talk about tipping points. It's a hot issue. I mean, for almost, precisely 20 years now, after a workshop in Berlin, I remember, we use the term tipping points in climate dynamics. It's an old term in sociology, but since 2005, we have it in climate dynamics. And this term, the tipping point, seemed to catch media attention much better than climate catastrophe or climate crisis. Huh? So it's a hot topic, but it's also actually a useful concept. I mean, generally, a tipping point refers to a point in time, or whatever you want to define, at which the forcing exceeds a certain threshold and such that the system or part of it transits into a new state, abruptly or slowly, and to some degree irreversibly. And we ought to understand these dynamics. And I think only the past offers the opportunity to test methods, to detect these points, and to study their dynamics. And today, it's a great pleasure for us and for me to introduce you 2 esteemed colleagues, experts and specialists in tipping points, Sebastian Battiani of the Technical University of Munich and Christo Boisert, sorry for misspelling, of Oregon State University. I had the great privilege of having Sebastian as a diploma student and doctoral student in Hamburg, where Sebastian received his doctoral degree with a great thesis on induced biome tipping points in the Holocene Sahara. Now, Sebastian uses approaches informed by dynamical systems theory, time series analysis, complex system models, and he's also a great speaker, which I witnessed, as he has a special passion for creative forms of science communication. Yeah, and Christo, he studied physics at the famous Delft University of Technology, and he got his PhD at the also famous Niels Bohr Institute in Copenhagen. And Christo is fascinated by ice cores and by unrevealing the information on climate dynamics, especially tipping points concealed in the ice using data analysis and numerical modeling. So we have 2 talks. First, Sebastian will present the paleo records, models, and dynamical system theory, Trinity of climate science or triangle of sadness. And then Christo will follow, and I will introduce the title then again. So, and after the 2 talks, which last roughly 25 minutes to 30 minutes each, we will have a lively discussion. And please do not interrupt the talks, but post your questions in the question and answer app of Zoom. So, Sebastian, then the floor is yours, please.
Thank you very much, Didier and Martin, for inviting me. I'm sharing my slides now, and you should see the full screen slide. And I'm trying to move away the Zoom panels to see something myself. Okay. Yeah, I'm, as Martin mentioned, so I'm interested in tipping points I don't consider myself a paleoclimatologist, but I run climate models to study tipping points. And so my presentation will be in a kind of review-like fashion, where I want to reflect a bit on, first briefly about definitions, Martin also brought up, and then I want to look at different approaches, how maybe different disciplines, how tipping points are perceived from the perspective of mathematical theory, from complex climate models, and also the data side, paleo records, or also observations. And then I will contemplate on the links between these disciplines and how they might benefit from each other, and what are recent developments that I am aware of and that I find interesting. So Martin gave already a nice definition of tipping points, and also mentioned a book by Malcolm Gladwell where this term got popular. And the subtitle of that book here, I'm not sure you see my mouse here. The subtitle is "Little Things Make a Big Difference," which is of course vague, and it's meant to communicate to large public audiences. And then ironically, now the scientists try to catch up with the term and try to define it more rigorously. And there are actually multiple definitions out there, which can sometimes be confusing, even in IPCC reports that generally, I think, do a great job and are very important. But you can also see that, for example, in the most recent report, how they define tipping point is a critical threshold beyond which a system reorganizes. The rest then is often abruptly and or irreversibly. So that's actually then not part of the definition, not necessarily, right? So it's just a threshold. And in the previous assessment report, ER5, that was a bit different, because there it was added and that the state of the system would not return to the initial state if the drivers are abated. So there's the notion of stable state and another stable state. So, and that is a mechanistic perspective. That is also reflected in recent review papers. For example, Armstrong-McKay, where it's required that there's some self-perpetuating mechanism. So these, and that's already an indication that there are different perspectives, and they can come from different disciplines, but we'll look at this more closely later. So let's start with the paleo side of the problem, where we see some nonlinear behavior. We don't necessarily immediately know why it happens, but I will come back to two examples throughout my talk. And the first is related to, well, what is then later was understood as linked to the ocean circulation, but in principle, you see in the ice core record in Greenland, you see these Dansgaard-Oeschger cycles with very nonlinear shifts between stadial and interstadial states of over time, and maybe even more clear in northern Africa some 1,000 years ago in the mid-Holocene, where the Sahara transitioned from a place with a much more abundant vegetation than currently, and animals, as these cave paintings show, and it changed to the barren desert that we know. And there seems to be, at least in the western part, a very nonlinear transition. So we can see that the response to the forcing, which is very gradual, is nonlinear with a large, relatively abrupt shift from more vegetated state to the desert state. So the other perspective from dynamical systems theory, so that's now really the toy model or conceptual model mathematical side. There we often fully understand the system at hand, but maybe not automatically the link to reality. But here the most common model is such a double-fold bifurcation, where you see what this AR5 report referred to. So there are two alternative stable states, and a stable state is a minimum in this potential valley. and the ball is the system state. And then when you slowly change the conditions and parameters of this model, then this state becomes less stable. Yeah, so the valley here is flatter, and then at some point it disappears, so the ball has to roll to this alternative state. That's called a bifurcation. And then what is very often then applied is then a behavior that is typical in such a model, which is called critical slowing down. So when this stable state becomes less stable, but it still exists, yeah, then the recovery rate to equilibrium from perturbations of this state, they become slower. And then you can see that in all kinds of indirect indicators of this recovery rate, for example, autocorrelation or variance, but there are also other ones. And then such a conceptual model, if you apply it to some cases where we wonder what happened, for example, Northern Africa or the ocean circulation, then this always is linked to a specific positive feedback. So this bifurcation is only possible because there is a strong positive feedback in the case. So if you want to apply it to the end of the Green Sahara, such a feedback could be between precipitation and vegetation because they can amplify each other, or in the case of the Dansgaard-Oeschger cycles and then actually the AMOC circulation in the North Atlantic. So that could be the salt advection feedback, where you have a circulation that brings salt, transports salt with it, and when the circulation is weaker, you advect less salt, and then the sinking is weaker because the density is lower, and then the circulation again is reduced. So that you always need such a positive feedback to get a bifurcation in these simple models. The third, let's say, discipline, yeah, let's say the corner, and that's actually the only source of detailed information that we get about the future, because we are interested, can such an event, can a tipping event also happen in future? So we need to also use models, complex process-based models, as much as we can. And what do these models show about future projections? You can look automatically use algorithms that filter through this large data sets. So this on the left is an example of a scan for CMIP5 models, on the right CMIP6 models. In principle, there are some common patterns, and that is mainly that abrupt shifts. So events where over a decade, for example, you have much larger change than usual. And these events, they occur mostly in the high latitudes over the ocean, but also some over land. And that is usually related to the freezing point of snow and ice that melts. So this is not necessarily related to bifurcations or feedbacks I mentioned earlier. So we already see there is possibly some disconnection. So we can now compare from different perspectives. So we have the theory side of the problem here that is related to feedbacks, to methods, to slowing down indicators, stability. Then we have more the phenomenological side and examples from the paleo record, and we have complex models. So I want to, from each corner, I want to now look at one of the other corners, and we can start with possible links. So what can we learn when we bring together dynamical systems theory, bifurcation theory, with paleo records or observations? And first of all, I think this comparison makes us aware that there are advantages and disadvantages in terms of terminology, or in terms of what's the useful definition. And that is, of course, a matter of taste, or it's subjective. You can define a tipping point as you wish, but in my perspective, what we learn from the paleo record is often that we see that some response is clearly nonlinear, but it might be very hard to figure out what the mechanism is. And maybe you want to define if it's a tipping point already before you know all that. The same applies to complex models when we see abrupt shifts and we don't yet really understand why. So I think a phenomenological perspective and of course, tipping points, they are mostly the most evidence we have is from the paleo record. So I think it's useful to apply such a phenomenological definition that does not rely on mechanisms too much, but yeah, that's my personal perspective. So how can dynamical systems theory or how can paleo research benefit from the theory? One point is that, so these, what I call CSD critical slowing down, for example, the slowing down of this variability around the potential well, and that occurs, so in case you have a system where the feedbacks weaken and you have a destabilization, in that case, we would expect these CSD indicators to occur. So you can, in principle, use them to assess, so to look in a record, do they occur or not? And you might have some evidence for or against the mechanism of a bifurcation, or at least some destabilization. So this was done in one of the first studies using slowing down in paleo record. Of course, there is a danger because people might have looked at other paleo records, but it's not published. So there's this publication bias that one should be aware of. And then one can, in principle, use the records to the present day and try to use slowing down indicators as a warning signal. So to see, is a part of the Earth system destabilizing or not? And that is done a lot currently. And I think there are some assumptions involved from the theory side that are not often checked. So I think there is some progress now. And one is, one can actually check the consistency between different indicators that are theoretically equivalent, but you can check in practice if they are, so if the system agrees with the theory or not. And then there are a lot of practical problems. So when you look at observations, there are, for example, different satellite records that could be merged and that affects these indicators, that gives you a bias, or especially paleo records, they have not equidistant sampling, they have gaps, there are outliers, all kinds of these things. So, and then there are also indirect variables, proxies or fingerprints. For example, for the AMOC, we use indirect evidence from SSTs, but we didn't observe the AMOC directly, and this comes with uncertainties. And then there's recently some studies try to extrapolate the trend of stability indicators, which then inherits these uncertainties. So I will show 2 or 3 examples about that. This busy figure on the left shows such a consistency check, where on the horizontal here you just have many different data sets that are meant to represent vegetation properties like biomass or also optical properties. And then you can estimate several different estimators of stability, and you can also estimate so an empirical recovery rate after large perturbations and compare with the diagnosed stability. So essentially, the correlation between them here on the vertical axis shows how consistent is the data with the theory. Yeah? And you see that some data sets agree better than other data sets. It's like a kind of benchmarking. Also here on the right side, you see an example how gaps in time series, how much they can affect the result. So this is a similar consistency analysis in an ideal system without data gaps. And these 2 indicators on 2 axes, they would be equivalent. So here, at least in the upper right, the data should sit exactly on the 1-to-1 line, the green line here. And then here, this orange line is the theoretical lower bound. So it should stay close to this orange and the gray line. But instead, when you only have 20% missing values, which is not so much when you think of some kind of records that have even more, you only have, you hardly have any correlation left. So these indicators then really don't work so well. Just to emphasize that it's not just the existence of gaps, but also the proportion of gaps that can differ between different locations, and it can change over time. So this is the amount of SST observations over time here in the subpolar gyre that you see here. And this non-stationarity that also induces bias stability indicators. In principle, this can all be taken into account. So that's good. Of course, the uncertainties don't go away, but you can quantify them. What does it mean for projected times of tipping? So we see there's a destabilization of the AMOC. And when you consider these uncertainties, what does it mean for, if you assume, yes, there is a tipping point, when will it happen? And you actually see here, you see different SST data sets and different kinds of fingerprints of how to translate SSTs into ocean circulation. And when you do that and include all these uncertainties, you see here a range year 2000 to year 5000, and the results span this entire range. So I would say that is much less or much more uncertain than previously acknowledged when you consider these uncertainties. The situation is, in this sense, much better when we look at complex models, because there you have regular, precise data. Of course, the models may be flawed, but these kind of problems don't occur. So these models are a great chance to actually study more fundamental conceptual limitations or challenges. And one conceptual challenge is the spatial complexity. So in this simple concept model that we saw with the bifurcations, you only have one state variable. In a more complex model, you have many grid cells, for example, here indicated as these 4 cells. You could have a very large scale tipping point like the ocean circulation that connects very different places. You could also have, and maybe more relevant for land vegetation, you could have interactions between different cells, and maybe some are less stable than others. Maybe, so this is the third case, which I call induced tipping. You have tipping in some area, and then another one passively relies on it, so it will also collapse, but you would not see a warning sign there, because this just passively follows the red tipping element. And you can also then think of this as impact tipping. So you have other systems that depend on the climate, but they don't affect the climate, like socioeconomic systems. Well, they also affect the climate, but not so directly. So this would also be then a shock for these systems that are impacted. You don't have to think of it in terms of grid cells. You can also think of different tipping elements on the globe, for example, AMOC or the Amazon rainforest. Also, West African monsoon depends on the AMOC. And these are coupled, so the transition in one tipping element can then delay or advance another tipping element. What I particularly want to stress is, in a way, this theory, so the dynamical system theory, is already a model, right? It's a very simple conceptual model. Our Earth system models are much more complicated models, but in principle, you can try to build a hierarchy and then see where dynamical systems approaches still work, where do they break down, and why. So that's such an example in a vegetation model, LPJML, where I looked at the carbon cycle in that model, and how does the recovery rate, the stability of the system, what can affect it, and can we diagnose it as predicted by the theory. So this is a very simplified LPJ model where you only have 4 state variables. It's different carbon pools. You can think of this as an idealized tree here with leaves and roots and stem. and hardwood, and you put in some carbon that you distribute into these components of the tree, and then the carbon gets lost again when the tree dies, for example, or when the leaves fall down. And here the crucial parameter I focus on is what's the fraction of the carbon that we put in the long-term pools, this sapwood or the hardwood, in contrast to the fast pools like the leaves. And then here in this figure, which is again a consistency check. So here on the horizontal, you have the true stability, that's the recovery rate of the system that you can directly measure in this model. The vertical is what you could observe in reality, is the autocorrelation-based estimate. Ideally, they would all lie on this red one-to-one line, so the aspect ratio is distorted here. In this model, they don't, but they still correlate if you look at this cloud here. But when I change this AS parameter, so the allocation to the slow pools, then we would actually move along this vertical axis. So the autocorrelation would change and give us a fake warning signal, although the true stability here on the horizontal would not change much. So it's kind of a contrived example, but it can have relevance in reality. So we need to know a bit more about reality than just how to apply the statistics. Okay, finally, I think also very relevant and maybe still a bit underused is then how can, for example, paleo observation or paleo reconstructions of tipping, how can they improve our complex models? How can they constrain the possibility of future tipping? And I think a very informative and impressive example is this paper by Hopcroft and Valdez, where they look at the Green Sahara problems and transition during the Holocene, and by comparing different model versions with different parameterizations, they can kind of tune the model by finding different parameterization that makes this vegetation cover transition from high coverage to the desert, make it closer to what we see in the record that I showed before, the dynamical sediment record. So here we see a nonlinear transition in this new specially parameterized version of the model. So that is in principle, of course, promising. On the other hand, this is very tricky to achieve because essentially these models are very hard to parameterize. So here's a little illustration. The way I think about it is that these models are very complicated machines. Yeah, we have a lot of levers. Of course, we understand the fundamental equations we put in, but the tipping is an emergent phenomenon. So, and we know that these models have biases, especially such nonlinear features like tipping points. They could happen or not happen, depending on slight changes. And then we have a lot of possibilities how to set parameters in the system, for example. And we can try what happens, but that is very expensive, right? So it takes a long time to run the model and it costs something to run the model. Then we get a result, but we cannot test the result directly against observations because it's about future tipping we have not observed. So in some sense, that reminds me of the Hitchhiker's Guide to the Galaxy, where people built a supercomputer, and this computer deep thought, it thought millions of years and got the result 42. And only then people realized that the question they asked was ill-posed, so they could not use the answer. And I think it's a nice analogy of this problem that we have. So I think we need also better methods for analyzing the models and maybe see how we can make them more or less stable, maybe even without knowing what is more plausible, but just exploring what the model can do. And we also need more flexible models so that we can tune them more objectively. So an example for the first case or method, this was one of our master students who implemented a method, and that works on typical Fortran type climate models, though they should be fast, so not the slowest models, but they don't have to be differentiable or anything. You just run the models, but you have to, so you fit a simpler model that is essentially like the conceptual model I showed earlier from dynamical systems theory. And based on that, you can decide how to change parameters to make it less stable. So you stop and then you change the parameters, then you run the model again and you repeat that, and then you will get, based on critical slowing down indicators, you will get a model version that is less stable. So here it's an example for a simple 5-box AMOC model, where the initial parameters give you a response to housing that is like this red line. And then the final destabilized model that you get is this black line. And also the hysteresis, that's not shown here, but the hysteresis of the model is also wider. So you can relatively efficiently find a less stable model version. And then, even a step further, it would be great, of course, to then also find a way to more efficiently and objectively calibrate models using some data. And that would work when the model is actually differentiable. So you can compute derivatives of the model and can then use a kind of gradient descent method using some data and find parameters where the model, for example, matches the data better. And so that would lead to a number of applications like easier calibration, uncertainty quantification. It can also be much more compatible with machine learning approaches of some components. So better data model integration. Right, so in light of these examples and thoughts, I would conclude that in principle, I think these three perspectives or these three disciplines, they can really benefit each other and they can work together to constrain the possibility of tipping in the future. Second, I think there's a lot of progress about more reliable stability indicators. So not just autocorrelation or so, but there are a lot of assumptions you can actually alleviate and get rid of with better indicators. So that can work. What still needs to be done, I think, is what I mentioned is model hierarchies. Many people talk about it, but it's not done so much. Closer. Oh yes, so that I didn't really mention, but it's what also should be done to connect data and models better. Sometimes you have variables only in the model or only in observations, but they are not comparable. And then what I mentioned last, differentiability of so more flexible models, for example, differentiable models would connect these worlds better. So there's a lot to do still, also to be published in Climate of the Past, for example. So happy birthday and thanks for your attention.
Yeah, thanks a lot, Sebastian, and also thanks for the nice birthday greetings and the great talk. Yeah, as mentioned earlier, it's now time for Christo to give his presentation, and as I mentioned, Chris is interested in data and also modeling, and Christo will provide us with an updated framework of global oceanic coupling of glacial abrupt change and ocean heat valve.
So I want to say good morning, good afternoon, good evening, whatever time zone you happen to be in. It's a real pleasure to be here today. I first want to thank the organizers, Denis and Martin, for inviting me and organizing this session. And I also want to say happy birthday to our favorite journal, Climate of the Past. The journal is now 20 years old, which means it's almost old enough to have a drink here in the US. So over this time, it's really established itself, I think, as a leading journal in paleoclimate. And that's a real testament to the hard work of the editors and also all the authors, to all of us who submit our papers there. So Sebastian and Martin already did an outstanding job in introducing the concept of tipping points. When I think of tipping points as a paleoclimate researcher, as an ice core researcher, Danskart-Oeschger events truly are the prime example of such behavior. In all my slides, time is going to go from the left to the right. I hope you can see my cursor here. So Greenland temperatures plot here on the top as the water isotopes in the Greenland ice cores. And what you see in these ice cores is a series of very abrupt switches, where the temperature in Greenland goes from the cold state, or the stadial, to a warm state, or interstadial. These transitions are abrupt. We're talking about 10 years, and they're large. We're talking about 10 to 12 degrees Celsius within a decade or something. So these truly are extremely abrupt events. This middle graph here shows the concentration of methane as measured in an ice core in Antarctica on the other side of the world. And this is really mind-blowing to me, right? So we have the water isotopes in Greenland, the methane concentration as measured in an Antarctic ice core, and there's a one-to-one relationship there. Every little wiggle you can see in the one is also visible in the other. And that really shows you that these events are not just something that happens in Greenland. These are truly global events. In this case, the methane reflects changes to the hydrology in the tropical regions. So what is driving these events? I think this is fairly well established at this point. These Danskart-Oeschger events are linked to changes to the AMOC, the Atlantic Meridional Overturning Circulation, which consists of this northward branch of warm water. When this water gets to the Nordic seas, these waters cool down, become very dense, they sink to the bottom, and this return current here at depth is shown in blue. This is an old figure from Stefan Rahmstorf that argues that these DO events are linked to abrupt switches in the state of this circulation. So in the warm stages where Greenland is warm, or the interstadials, this Gulf Stream, or this AMOC, can go very far north into the Nordic seas and sinks and sort of provides very deep sinking waters. Whereas in the off state, this AMOC current is much weaker, providing less heat transport to the high latitudes and cooling Greenland. So this has been well established for quite a while. However, this is still extremely relevant. What I'm showing here on the left is a figure from the most recent IPCC report, where they compile different models and their response to future warming. And what you see is that overwhelmingly these models suggest that in the future we can expect to see weakening of this AMOC current. Even Hollywood picked up on this theme with that famous disaster movie, The Day After Tomorrow. But this really provides great impetus to study this problem better. For me, one of the main things I'm interested in comparing the paleo record to what we may expect in the future is whether this is more what we're seeing in the future, whether this is more of a transient weakening that is just, as I said, transient, so may be resolved, or one of those tipping points where we're collapsing to a new stable state with a weaker AMOC. And this is something maybe we can take up in the discussion after the sessions. So what I want to focus on today mostly is the global coupling of these DO events, right? These have a global impact, and most famously, this impact is reflected in Antarctica. What we see in Antarctica is shown in this bottom graph here in purple. This is the waste divide ice core. What we find is this out-of-phase relationship that is commonly called the bipolar seesaw. What happens during periods when Greenland is cold, we see gradual warming in Antarctica, as shown here by the red arrows. During periods when Greenland is warm and this AMOC current is very strong, we see gradual cooling in Antarctica, right? So this is not just something that happens in the North Atlantic. This has global implications, and the record in Antarctica is very clear in establishing this global pattern. Well, this relationship has been known now for a few decades, and the most famous conceptual model that is used to interpret this is the thermal bipolar seesaw model by Thomas Stucker and Sigfús Johnson here from 2001. And this is the conceptual model they provide. They argue that what's happening in the North Atlantic is these abrupt switches in the AMOC, and I think this is still widely held to be the case. And then they suggest this drives opposite temperature anomalies in the North Atlantic and the South Atlantic, right? So if one is warm, the other is cold, and vice versa. This is the seesaw effect. Then they argue that the South Atlantic anomaly is not exactly what you see in Antarctica. Instead, this is buffered by a heat reservoir, right? Which they argue is likely the Southern Ocean, because that is what buffers Antarctica from the more mid and higher latitudes oceans. And so they call this model the thermal bipolar seesaw. The seesaw refers to this the dipole that you see in the Atlantic, and the thermal component is this heat buffering by the Southern Ocean. Most importantly, I think, is this last point here. They recognized that the signal that we see in Greenland, what they call TN here, the northern temperature, the temperature in Greenland is minus the time derivative of the Antarctic temperature, or TS, that they showed. So this is an important point to keep in mind. Okay, so this model is 25 years old at this point. And since that time, there's been a lot of additional developments, and I'm going to summarize some of them here. So some of the new conceptual insights include that it's not just the ocean that warms or cools, it's really a planetary phenomena, right? And so Eric Galbraith made this argument famously in a model paper, but also data papers have made this point. Joel Petro argued that it's not really the Southern Ocean that's the heat reservoir, it's really the global ocean, or at least the global interior ocean. Another development that I think is very important in that time is that we now have proxies for the mean ocean temperature or ocean heat content, right? We have proxies for ocean heat content we can measure in ice cores with extreme temporal precision. And we find that they broadly reflect Antarctica. And there's a couple of citations here. Sarah Shackleton has done a lot of this work, and Bernhard Breiter, but also the Bern group in Switzerland has done a lot of this work. So these are some of the conceptual advancements, I think. At the same time, the state-of-the-art climate models have really advanced. And now there are several models that can simulate spontaneous, self-sustained DO oscillations that are extremely realistic. And there are 3 examples here, and these are the ones that I'm going to be looking at in this talk. There's the Cosmos model by Zhu Zhang and co-workers, the Japanese MIROC model. Ayako Abeuchi has been doing a lot of this work, and one of her students published this paper in 22. And then there's the CESM model, or CCSM4, and I'm going to be using some model runs from Guido Vetteretti. So the goal of the talk here today is I want to give you an updated idea of this bipolar seesaw framework that includes these new insights. And we're going to use these 3 spontaneous DO models to evaluate this frame. So most of the things I'm going to say here today are not new. People who follow the literature very closely are going to recognize much of what I'm saying here. The idea here is to really put a bow on it and sort of put everything together in one frame. So let's first look how these 3 models perform in simulating these bipolar linkages. So as I mentioned, all 3 of these models have self-sustained DO oscillations that look very realistic compared to the observations, and they simulate very realistic polar temperatures. So here's the CCSM4, MIROC, and Cosmos models. These are the AMOC variations that they simulate. The middle line here is the Greenland temperatures, and so they look very similar to the observations, right? Really abrupt warming phases that are about a decade, and magnitudes of warming of up to, say, 12 degrees Celsius. So all these 3 models do a really good job in simulating Greenland temperature. When it comes to the Antarctic temperature, both the CCSM4 and the MIROC models do a really good job in capturing that triangular structure with warming occurring during the Greenland cold phases and Antarctic cooling during the Greenland warm phases. The Cosmos model, on the other hand, does not simulate the Antarctic signal very realistically, and we'll come back to some of those reasons later. So what about the classic seesaw, right? So the models get Antarctica right, they get Greenland right. What about this classic dipole? So the seesaw model hinges on this conceptual idea that the seesaw is operating in the North Atlantic. So what I'm plotting here is the surface temperature anomalies in both the North Atlantic and the South Atlantic. The North Atlantic anomalies very nicely follow the Greenland temperatures and follow this concept of the bipolar seesaw. The South Atlantic temperatures do not, right? They really do not show this dipole that you'd be expecting from this conceptual model. There's also no interhemispheric redistribution of heat. If you read papers on this topic, they'll often talk about the redistribution of heat. I've written this myself. If you go through my old papers, you can find plenty of sentences where I talk about redistribution. It's really not happening in these models. What I show here is the ocean heat content of all the ocean basins in both the Northern Hemisphere and the Southern Hemisphere. There's no redistribution of heat going on. They're changing in parallel. Right? So both hemispheres are losing heat or gaining heat at the same time. They're not redistributing heat between each other. So these are some of the points that I wanted to get out of the way quickly. And what I want to suggest is that the model that we should be thinking about perhaps is even simpler. Right? This top model is simple. I'm arguing, and so to keep in mind for the rest of this talk, maybe an even simpler model where the heat reservoir is just a simple box that represents the ocean heat content, or the total, it represents the global ocean, and the heat content of the global ocean gains its heat mostly in the Pacific and the South Atlantic, as we'll talk about later. That's where energy is input in the ocean. A lot of energy is lost from the global ocean in the North Atlantic. However, the amount of energy lost is variable. So this is where the heat valve comes in. Think about a valve that you can open all the way or open just a little bit. So this is, I think, a more accurate reflection of the physics of this simple system, and conceptually actually a little bit easier than the old seesaw. So the math, however, right, so the conceptual model by Stucker and Johnson also came with a very elegant equation that is actually extremely effective in capturing the observations. Lucky for us, the same equation can actually be applied to both systems. So the simpler system with just a single box responds to the same kind of math, and so that good fit to the observations holds for both conceptual models. It's just a slightly different interpretation in terms of the ongoing physics. So to dress it up a little bit more and make it a little bit more elaborate, I made this sort of conceptual model here. So the framework that we're going to talk about is centered on this ocean heat content. Heat uptake is primarily located in the Pacific and South Atlantic Oceans, which is shown here with this arrow, right? So this is the ocean, the single box ocean. It has heat content. Heat uptake happens here in the Pacific and the South Atlantic. Heat is lost in the Southern Ocean and the North Atlantic primarily. And so when we think about this ocean heat content, it can only change through the surface fluxes, right? If there's more energy incoming than outgoing, it will go up. If the outgoing energy is larger than the incoming energy, it will go down. Whatever happens here at the surface of the ocean has to be matched by the radiative balance of the entire planet. So whatever the radiative balance is at the top of the atmosphere has to match what happens in the ocean. And the reason is that our atmosphere does not have a very large heat capacity. The atmosphere cannot store much heat, so whatever comes out of the ocean has to be radiated out into space. So this is sort of the conceptual model we'll be working with. And I'm going to talk to 4 different principles to help us understand what's going on in the energetics of the bipolar seesaw. So first, the first principle here. So the AMOC is a heat sink to the global ocean. The ocean heat content increases during the stadial weak AMOC mode, and it decreases during the interstadial mode. So this is how that shows up in the models. I'm using the CCSM4 model here as an example, but they all work the same way. We have these spontaneous DO oscillations that are being simulated by the model. And this is now a look at the ocean heat content broken down by all the different ocean basins. And so when we see during the stages of the weak AMOC, we have warming in the global ocean, but also in all these different ocean basins. So ocean heat loss during the strong AMOC phases, ocean heat content gain during the weak AMOC phases. And I want to emphasize here that all the ocean basins have the same sign and the same phase of their oscillations. Let's look at the heat fluxes, right? So again, if you want to change the ocean heat content, you have to get heat out or in through the surface of the ocean. What we see here is again broken up by the different ocean basins. So these top 2 layers here, so the light blue and the purple, are the Pacific and the South Atlantic. And as I mentioned, the numbers are positive here, means heat uptake. These are the places where the ocean is gaining heat. And throughout the DO oscillation, this heat uptake is actually fairly stable. Then we look at the North Atlantic, here in yellow, and this is the most variable of all of them, right? So the heat loss in the North Atlantic is very variable depending on the state of the AMOC. If you add all of these together, you get this gray line. And you can see the gray line is really dominated by the Atlantic oscillations, right? And so, of course, this one has to be the time derivative of this one, right? And so whenever the ocean is losing heat, the heat flux is negative. So it's really the North Atlantic that's driving this heat loss. What I also want to emphasize is that all these ocean basins are gaining and losing heat, for example, the Pacific, but it's not because of their surface fluxes, right? So the Pacific is doing the same thing as the Atlantic. It's losing heat, it's gaining heat, it's losing heat, it's gaining heat. However, its surface fluxes are standard. So this is really due to internal ocean redistribution of heat. Now let's look at all the 3 models together. So here's again on the left, CCSM, MIROC in the middle, Cosmos on the right. And as you can see, they all have these AMOC oscillations, and they all have these triangular looking ocean heat content variations, right? They all look very similar. Cosmos, though, has a much smaller magnitude of these heat content oscillations. But the CCSM and MIROC models look surprisingly similar here. One thing to point out here is that the Cosmos model has some kind of a seesaw between the Atlantic and the Pacific. So during times that the Atlantic is losing a lot of heat, the Pacific is compensating by absorbing more heat. And this is the reason why these oscillations are much smaller in magnitude in this particular model, and also part of the reason why this model does not simulate a very good Antarctic response. So the takeaway here is, all these three models fundamentally do the same thing, right? The AMOC variations drive changes in the Atlantic heat loss, which drives changes in the ocean heat content. As I mentioned, these changes in ocean heat are propagated through the mid-depth ocean. So I'm going to start this video in a second, but just to orient you, here in the bottom left is our time marker. So we're going from the left to the right. We're looking at 6,000 years of simulations with the AMOC strength here, mean ocean temperature at the bottom. And there are 3 panels that show you the heat at different depths in the ocean. So the top left here is the surface ocean, upper 30 meters. This panel in the top right here is the intermediate depth from say 200 to 1800 meters. Bottom right is the deep ocean, deeper than 2300 meters. And so if I show this video, what you'll see, so now we get a AMOC weakening. And so now we get a warm anomaly here in the mid-depth Atlantic that propagates into the Indian Ocean, propagates into the Pacific. And over time, after maybe 1,000 years or so, the deep ocean also starts to catch up. Now we get a warming. So now we get a cold anomaly here in the mid-depth. It propagates to the Indian Ocean, to the Atlantic, and after a while, the deep ocean starts to catch up. Also happening at the surface, you really only see the North Atlantic, right? So the North Atlantic is a cold anomaly, or now it's a warm anomaly. You don't really see that seesaw that I talked about. There's no dipole in the Atlantic. It's really just the North Atlantic that's dry, where you see big SST changes, and that's driving these heat anomalies in the entire ocean. So here again, these mid-depth anomalies in the Atlantic are propagated to the Indian and the Pacific Oceans, and then over time, the deep ocean catches up. I have these videos for all the three models, and they again show very similar patterns. I also want to link it up with the data a little bit, and I want to get back to this oldie but a goodie from one of the founders of our field, Nick Shackleton, in 2000, and he has this really important paper, I think, where they cored off the Iberian margin of southern Portugal, and this is from their abstract, right? They say it can be correlated with Greenland ice cores. Oxygen isotope variability in planktonic foraminifera closely match the ice core temperature over Greenland, right? That's that same relationship between North Atlantic sea surface temperature and Greenland. However, the oxygen isotope signal in the benthic foraminifera is quite different from the planktonic record and resembles the temperature in Antarctica. Right, so that's the distinction here. So the deep ocean reflects the mean ocean temperature, which looks like Antarctica, whereas the surface ocean looks like Greenland. Okay, brings me to the second principle. These ocean heat content gains and losses at the surface are linked to the radiative imbalance at the top of the atmosphere. These two statements, 1 and 2, are very closely linked. You cannot have one without the other. You cannot have one without two. You cannot have two without one. But it really emphasizes that this is not just the ocean. This is a planetary heat imbalance phenomena. The entire planet cools and the entire planet warms. So if I take the same figure I had earlier, right? So this is the CCSM4 model again, with the AMOC oscillations on the top, ocean heat content at the bottom, in the middle. And at the bottom here, I've now added the heat fluxes at the top of the atmosphere. In blue, the shortwave, the incoming shortwave changes, and in red, the outgoing longwave anomalies. And so the sum, the balance of these two is that black line. And what you can see is during phases when the AMOC is strong, indicated in blue, when the AMOC is strong, the ocean is losing heat, but the entire planet is also losing heat. So this, the top of the atmosphere energy imbalance exactly matches what we see at the top of the ocean. So the heat flux at the surface of the ocean perfectly matches the heat flux at the top of the atmosphere. And again, they kind of have to, because the atmosphere cannot hold much heat, right? So it's really a planetary phenomenon. Let's dive into that a little bit deeper. So first, we're going to talk about the DO mode. So here's again a bit of a figure where we show the AMOC and the ocean heat content. The red dots here give you the interstadial times. The blue dots look at stadial times. So I'm going to be subtracting the two, and we're looking at the red one, the interstadial minus the stadial conditions. And this is what it looks like, right? So when we look at this DO mode, this plot here at the bottom shows you latitude, and here longitude and heat flux. What we see is a sea surface temperature, or we see a temperature anomaly, mostly focused here on the North Atlantic. The yellow line shows you the retreat of the sea ice edge. And what we have during these DO events, we get SST warming in the North Atlantic, we get sea ice retreat. At the same time, we get an increase in the incoming shortwave radiation. That's just the albedo feedback, right? We removed sea ice, we're exposing dark ocean, we're absorbing more incoming shortwave. At the same time, we're warming the high latitude northern hemisphere, so we have an increase in the outgoing long wave. And this long wave dominates, right? So the outgoing long wave is larger, and therefore we get cooling. Again, I also want to emphasize, none of these models really show that classic seesaw response that we normally associate with the bipolar seesaw. So next, we're going to look at the other mode. I'm going to call this the ocean heat content mode. So if we think about ocean heat content, I'm going to look at these purple minus the green. Maximum ocean heat minus minimum ocean heat. And this is what this one looks like. This one is mostly centered on the Southern Ocean. So this ocean heat content mode sort of outcrops there, right? The deep ocean outcrops at the in the Southern Ocean, and it also sort of associated temperature anomalies of the deep ocean are also outcropping there in the Southern Ocean. So what we see, if we look at the ocean warm mode minus the cold mode, its surface expression really is around Antarctica. So SST warming and sea ice retreat happen here in the Southern Ocean. We have, again, increased incoming shortwave, right? We're removing some of that sea ice, we're exposing dark ocean, so we're absorbing more incoming shortwave. But we're also increasing the outgoing long wave a little bit. In this case, though, the shortwave dominates. In other words, the albedo effect is a little bit stronger, so the ocean, or the Antarctica, absorbs a little bit more heat. This planetary heat imbalance has also been seen in observations. This is a paper from Daniel Bagenstos from, I think this is 2023 or something like that, where they combined mean ocean temperature data with sea ice, global ice volume records to reconstruct the planetary heat balance. And so wherever it's positive here, they find that there is a positive balance, meaning that the Earth gains energy. And as they show here, it is very strongly linked to the state of the AMOC. When the AMOC is weak, the planetary energy balance is positive, right? So the observations and the models really clearly agree on this point. Okay, and this is the time I gotta go a little fast. The third principle here, the Greenland and Antarctic temperatures mirror the North Atlantic heat loss and ocean heat content, respectively. So let's talk about this one. Like, why do we see the signals that we see in Greenland and Antarctica? I'm trying to explain it here on the left with this figure. This is a bit of a complicated one. So there's 8,000 years of model simulations here. This top panel shows two different things. In green, I show the Greenland temperatures as simulated by this model. In gray, underneath it, is the integrated surface heat flux for the global ocean. All right, and you see an extremely good correlation because the global ocean heat flux is really dominated by the North Atlantic. And so when the ocean is losing heat, Greenland tends to be warm. When the ocean is losing heat, is gaining heat. Am I saying that right? Yeah, Greenland is cold. So the bottom curve here shows Antarctic temperature in purple and the global ocean heat content in gray. And again, a really good correlation between those two. Again, this is related to the fact that Antarctica is surrounded by the Southern Ocean, so that any temperature anomalies in the interior ocean are outcropping at these southern high latitudes, reducing the sea ice and impacting Antarctic temperature. So I'm going to go back to my simple cartoon of the global ocean here. And there's these little markers here. So for some things, I gave them little green triangles, and some of them have little purple asterisks. And these talk about correlations. So all the things that have the green triangle next to them are really strongly correlated. In other words, the strength of the AMOC is really strongly correlated with heat loss from the North Atlantic, really strongly linked to sea ice extents in the North Atlantic, really strongly correlated with Greenland temperature, and very strongly correlated with the heat flux at the top of the atmosphere. On the other hand, the ocean heat content is the purple one, right? So it's very strongly correlated with the heat flux out of the Southern Ocean, strongly correlated with the sea ice edge in the Southern Ocean and with Antarctic temperature. I started off, 10, 15 slides ago with talking about this relationship between Antarctica and Greenland, with Antarctica being minus the time derivative of Antarctica. When we think about it in these terms, that relationship is very natural, right? Of course, the heat flux out of the ocean has to be the time derivative of the heat content, right? So this observation is quite natural with that simple model. And in all these three models, these observations, this relationship seems to hold quite well. I have a figure here putting some numbers on that. I'm not going to go through that in the interest of time. Okay. So what about the data, right? So what I'm suggesting here is that Antarctica simply reflects the mean ocean temperature. We now have really good observations from the ice cores of what mean ocean temperature looked like. And I show you here two figures from two different papers. This is a paper from Sarah Shackleton in 2021 with the mean ocean temperature that she reconstructs on the horizontal and the Antarctic temperature on the vertical for different time periods. And you see an extremely strong correlation there between mean ocean temperature and Antarctic temperature. On the right is a more recent paper by Marcus Grimmer from 2025, where he looks at 4 different terminations, and he finds the same pattern. On the horizontal here is the mean ocean temperature that he reconstructs using the noble gases. On the vertical axis, the Antarctic temperature. Again, a very strong correlation between these two parameters, right? This is exactly what the models suggest, and it's due to these processes in the Southern Ocean. Okay, the last principle is the dependence on the background climate. And what it basically, I'm kind of, Martin, Denis, how am I on time? Do I have time to go through this?
No, well, 2 or 3 minutes.
Yes.
2 or 3 minutes, okay. I'll keep it, I'll just show this slide. I'll just show this slide and the next one real quickly. So these are observations that is from 2 papers here, one that I wrote with Andreas Schmiedner in 2015 and one that I wrote with Ed Brook in 2018. Where we looked at the relationship between the duration of the interstadial and the temperature in Antarctica, right? And what we find is that there's a very strong relationship. When Antarctica is warm, the duration of these interstadials tends to be very long. When Antarctica is cold, their duration is very short, right? I also try to illustrate it schematically here on the right. So in warm climate periods, which is marine isotope stage 1 or the Holocene and stage 5, we have a much more stable AMOC, which results in very long interstadial durations. During really cold stages, such as MIS2 and 4, periods with low CO2, this interstadial mode is very unstable, right? And so if we do get a DO event, it only has an interstadial duration that's very short. That's what the data show. And the models confirm this. This is a study by Guido Fetteretti in 2023, where he shows that by increasing CO2, you really fundamentally change the character of these oscillations. When the CO2 is low or when it's cold on Earth, the AMOC is stable, but it stays in this off mode, in the weak mode. On the other hand, at the top of the figure here, if the CO2 concentration is high, the world is warm, you again have a very stable AMOC, but now it's stable in this strong overturning mode. For these intermediate states, you get oscillatory behavior, but what you see is a dependence of the interstadial duration on the CO2. So as we go down in this figure, lower CO2, the DO events are shorter in duration. Going up in the figure, the DO interstadials are longer in their duration. And so I don't have much time to talk about it, but this energetic framework that we're proposing here really provides a very sort of simple, intuitive explanation for this behavior. So I'll just come to my summary and conclusions then. So what I did here is look at the energetics of the bipolar seesaw in these 3 models. So the bipolar seesaw reflects variations in the global ocean heat content. The AMOC acts sort of like a heat release valve, right? When we have a strong AMOC, the valve is all the way open. We're losing a lot of heat from the ocean, but also at the top of the atmosphere, right? So the heat content changes of the ocean are one-to-one linked with the heat imbalance of the planet. The Antarctic temperature is correlated to ocean heat content. The Greenland temperature is correlated to the global heat flux. And with these very simple principles, I think we can explain a lot of the observations that we find. So thank you very much.
Yeah, thank you very much, Christo. And also warm thanks to Sebastian. Now the floor is open for questions. And as I said earlier, please put your question in the question and answer box. And I think Denis and I will read the questions one after the other and try to get an answer. Maybe I start because there's the technical question from an anonymous. Hello, sir, please, where we could find the recording session. So that's, I guess, a question to Eduardo, our manager here. Or do you know
the recorded session will be on the EGU webinar page, so it will be available. Yeah.
Okay, so that's then answered, and then maybe so then you go ahead with.
Yes, there is a question by Fabrice Lambert about how do the winds respond to increased ocean surface heat fluxes? Any positive or negative feedbacks?
Is this a question to me or to Sebastian?
I think it's both of you.
Yeah. So in these model simulations, I haven't, to be honest, I have not looked at the winds too much. Are you particularly thinking about the winds in the North Atlantic or the Southern Ocean, for example? To be honest, I haven't really analyzed them, so I don't want to go on record saying anything that's incorrect.
But Sebastian, so no.
Actually, there's a second. Okay, Sebastian, do you want to say something about the question about ocean flux?
Yes, I don't know the answer to Fabrice's question.
Okay, good.
But yes, I accidentally answered, but I had a new question.
Okay.
And I was wondering, because I heard, at least in a conceptual model, there is a heat reservoir underneath the sea ice in the northern hemisphere, so where the heat accumulated until it was warm enough that the sea ice goes away, and that's when you get this sudden increase in the temperature. Is that some kind of heat reservoir that happens in these ESMs?
Yeah, this happens in the models too, right? So as you're so over time, when you have let's start off with the weak AMOC. If you're in a weak AMOC, see if I can find the. Am I sharing my screen right now? I think I am.
Yeah.
Let's see if I can find a relevant figure here. Maybe there isn't a relevant figure. Oh. Yeah, so that is a mechanism that happens in the models, right? So when you turn off the AMOC, you have a cold lens on top. You know, you extend the sea ice, you have cold, fresh water on top, but it's really a very shallow layer. It's only really the surface ocean. What you do is over time, you build up this temperature anomaly at the mid depths. So in the mid depths, you're building up this heat reservoir in the mid depth North Atlantic, and that erodes what do you call that word? It erodes the stability of the water column, right? The stratification of the water column gets eroded by having warmer water there. So as that reservoir warms up underneath the sea ice, that intermediate depth reservoir warms up, it destabilizes the water column, removes the stratification, and allows that the warm states to persist. Yeah. So yes, these dynamics that you're referring to do happen in these models.
So, question to Chris from Lev Tarasov. How does your framework explain bond cycles and apparent synchronization with Heinrich events?
Yeah, it's a good question. The bond cycle. So far in this model, let me see if I can find the right figure. Yeah, let's talk about this slide, right? This one, yeah. So the astute observer may have noticed that I cut something off this figure, right? If you read the original Rahmstorf paper, there's actually a third panel there where the AMOC is off. So far, I've really only talked about the two AMOC states, the strong interstadial and the weak stadial mode. There's a third mode, which is the Heinrich mode, during which there is ice rafted debris, probably lots of iceberg discharge into the North Atlantic that further suppresses the AMOC. So I didn't talk about it here because these models, these self-sustained oscillations, do not really have Heinrich events. Guido Vettoretti wrote a paper where he also applied additional hosing. So during the there's a natural oscillation. During those cold stages, you can apply additional hosing to further weaken and further suppress the AMOC for a very long period of time. Right, that's sort of that's simply the same principle that I'm talking about here. So you can extend this to include this third state of an additionally weakened AMOC. What happens if you suppress the AMOC for a very long period of time? You build up a lot of heat globally. What happens if you build up a lot of heat? Now, you know, that fourth principle that I outlined, if the ocean is very warm on principle, you can sustain the AMOC very, very long amount of time. You can think about it as an energy balance. It just costs energy to perpetuate the AMOC. So if the Earth is very warm, if the ocean is very warm, you can sustain that AMOC for a very long amount of time, right? So after you've had your Heinrich event, you've built up a lot of excess heat in the ocean, which means that first DO event that happens can be very long in duration simply because you have so much heat built up. Now, throughout this cycle, you progressively start to lose some of that heat. So subsequent DO events are shorter and shorter and shorter and shorter in duration because you're losing that heat. You're also reducing CO2 at the same time. So I think from this model, you can understand the bond cycles as some sort of a damped oscillator. You build up a lot of excess heat in the ocean by suppressing the AMOC for a very long amount of time. And this heat is then gradually lost again over a series of DO events that get shorter and shorter and shorter as the ocean gets colder and colder and colder. I've been asking Ayako for, maybe I think Ayako is here in the audience. I've been asking her for 3 years now to simulate this, and I don't think it's a lot of work to do this, so I understand why she hasn't. But I think intuitively, to me, that is the explanation behind the bond cycle. But I think what is needed is for somebody to really do this in one of those self-oscillating models. And here I'm putting Ayako on the spot publicly. Sorry for doing that, Ayako, but I think it's a really an experiment that's worth doing.
Okay, we start with the first question by Nick Horseshoe. So that is a question to Christo again. Christo, fascinating talk. I'm interested in the atmospheric response. I know you say that it has low heat capacity, but to drive the radiation imbalance of the atmosphere and produce net energy loss. Does the atmosphere have to warm? So you say I
was being a little sloppy in my language there. Of course, the atmosphere has a heat capacity. It's just the fact that if you compare the heat capacity of the atmosphere to the heat capacity of the ocean, it's negligible, right? It does have a heat capacity. And so, yes, it does warm. So if you look here at this temperature, I wasn't maybe clear enough. This is not the sea surface temperature. This is the atmosphere, right? This is the air temperature, not the SST. That's why it's also over land. So when you have a DO event, you warm the surface North Atlantic, you increase that heat flux out of the North Atlantic that warms the atmosphere. So you warm the northern hemisphere, high latitude atmosphere, as you see in this figure very clearly, right? So the warming extends all the way over Greenland, over North America, over Europe, but all the way into Beringia here as well. So you get atmospheric warming across the northern hemisphere, high latitudes, and that's what's driving this outgoing long wave radiation. So Nick, you're 100% correct, right? The atmosphere does have a heat capacity, and it actually needs to heat up to increase this outgoing long wave. Yeah.
So still a question to Chris. Has the bipolar seesaw model been tested on any other type of terrestrial climate records? If yes, is there any time lag between the ice cores and the terrestrial records?
Yeah, that's a good question. So the terrestrial records. So first of all, I don't think there are any terrestrial temperature records per se that are of sufficient, resolution to really time resolution or time precision to tell us much about these events. However, the records that do have the terrestrial records that do have the best age control are, of course, the speleothem records. And these speleothems typically record hydrological changes, right? So what I show you here, for example, is these are ice core data. So the black line here is the temperature in Greenland. The green line is the global methane concentration, and the global methane concentration is linked to hydrology. To produce methane, you need to have wetlands. To have wetlands, you need to have rainfall. In these tropical regions, we also have lots of speleothem records, like cave deposits, and those also record the rainfall, the hydrology of the region, and we find very close relationship. And I think it was Ellen Corrick, I think, was the first author on this paper. They did a global study where they looked at these speleothem deposits from around the tropics and really convincingly showed that they, in terms of their timing, are completely synchronous with these events in the AMOC and in Greenland. Come to think of it, that Corrick paper actually also has some Mediterranean speleothem deposits, which actually do probably record local temperature, right? The temperature through the rainfall. So yes, we have terrestrial records, both of temperature and rainfall, that really show that this is a globally synchronous event.
If I can add from my own expertise, in the European loess deposits, when you have these abrupt warming in Greenland, you have paleo soils which are developing in the continent.
Wow.
And
Great.
when you
And also,
when you have the stadial conditions, then you have aeolian deposition.
yeah, and that's actually the new record from the Sahara, the Lake Yoa record. It's hopefully going to be published very soon. Also, it was drilled in 2010 or something like this. And then, okay, it goes only back to 10,000 years. I mean, but we see a clear 8.2K event with the reduction in info. Okay, yeah. Now, next question from by Ibrahim. Christo, from what I understood, the ocean heat content seems more correlated with the AMOC. Is there no effect on ocean atmosphere coupled systems like MGO, ENSO, and so on the internal redistribution of heat? What's the effect of upwelling as well? This is Ibrahim, a meteorologist, by the way. Thank you. And as I asked the question, I'm also a meteorologist, and I also have experimented with the climate model, and we see using Hofmüller diagram also the motion of heat through the ocean. I guess it's also related to what Ibrahim. So what about legs and leads and heat content and MGO and
yeah, so these are really, really good questions. And so to be clear, right? So these models have a wealth of information in them, and I have not mined all of it, right? Just the things we've looked at are just the data that I have shared, that the modelers share with me, are decadal means, or some days even 50-year means. So the goal of this project, the modelers, a little bit of backstory, the modelers and I got together in Rome during the INQUA meeting. That was, I think, in 2023. And we just agreed on sharing sharing the same parameters between all the models. And we were looking at decadal means. So when it comes to these higher frequency modes of variability, extremely important, extremely interesting. I have not looked at them, right? And so I think this is just a starting point. We're trying to understand the large scale energetics of this oscillation. I have not looked in depth at those phenomena. I'm also, this is not necessarily my personal research focus. I would just encourage anybody to get in touch with the modelers of this paper that are included in this study and do that work. It's something that needs to be done, something that I haven't done, something that I also don't have time to do, to be frank. But I think it's something that should be looked at. So that's a very disappointing answer, I know, but I just haven't looked at it.
So can we move to Sebastian? There is a question from Laurine Grégoire. Does critical slowdown apply to Greenland ice sheet tipping?
Yeah, good question. There is a study, I think Börs and Drupta 2021 in PNAS, that finds in, I think it's a meltwater record somewhere in western part of the ice sheet. So they analyze this record and they find indicators of slowing down. I think, yeah, the mechanism why that happens is a bit open to interpretation, because the typical feedbacks that really make ice sheets potentially bistable, that lead to self-amplified ice sheet loss, are melt elevation feedback, and then when the ice sheet is really almost gone, also ice albedo feedback. But this melt elevation feedback, I guess it works on very long time scales, because the change in ice sheet height, fluctuations in that height, that has a very long time scale. So I'm not sure that is the reason why we see slowing down in that record over some years. So I think that's a good question to be further investigated in all kinds of models also, to work out what are warning signs that are useful on the timescales we can observe, so that I can't give a final answer.
Okay, yeah. So then we've got a question to Christo by one of our dear colleagues and co-founders of Climate of the Past, Eric Wolf. And he asked Christo, can I just clarify how your explanations relate to Antarctic temperature? I have tended to describe the link between Antarctic temperature and deep water temperature as an Elderfield 2012, as Antarctic temperature sets the global ocean temperature. But that's really wrong, isn't it? I should be saying it's the other way around.
Yeah, of course, I hesitate to go on record as saying that Eric Wolf is wrong about anything. But so this is what the model. I'll just tell you what the model says, Eric. So this is the figure that I skipped. So in the interest of time, so let's look at the left panel here. So what I tried to do in this figure is to isolate the heat fluxes in these models when we're comparing the maximum heat to the minimum heat, right? This is the warmest phase of Antarctica minus the coldest phase of Antarctica. We're talking about anomalies here. So when comparing those two, we see that the ocean heat content increases by quite a big amount, like half a degree Celsius of ocean heat difference between that maximum heat state and that lowest heat state. What we see in the difference here is that the heat flux is out of the ocean. When the global ocean is warm, the heat flux out of the Southern Ocean increases, in this case by about 70 terawatts. What happens at the same time, of course, as the ocean warms, is that the Southern Ocean sea ice retreats, in this case by about 1.5 degrees of latitude. This leads to a shortwave albedo feedback, right? So we're replacing white sea ice with dark ocean. So we have an increase in the absorbed shortwave radiation, in this case about 130 terawatts. But also because we're warming the high latitudes in the southern hemisphere, we're also increasing the outgoing long wave. In this model, that was by about 100 terawatts. So if you add this all up, what happens during these warm phases is really I think it's the ocean that warms Antarctica, right? The heat is out of the ocean, not into the ocean. So during these warm phases, the Southern Ocean heat flux increases, which then has some feedbacks in the atmosphere. The totality of those things tends to warm Antarctica. So I would say, yes, it is the ocean that warms Antarctica. It is not Antarctica that sets the temperature of the ocean. Because the ocean gets its heat in the low latitudes. The ocean gets its heat in the tropics, and it's losing its heat in the high latitudes.
So there's only, well, I would have a question to Sebastian, but I'm not sure how to type it into the but because there's only would be for you, Denis, but that's not a question by Ayako. It's just a comment, no?
Yeah, I'll follow up with Ayako and
okay, good. Yeah. Okay, so then may I take the liberty of asking Sebastian, because I didn't understand your title of the talk. I mean, you say records, models, and theory, Trinity of climate science or triangle of sadness. I mean, wow. There's no way out to use this Trinity, isn't it? I mean, if you have records, I mean, yeah, playing with records doesn't explain your physics. You can guess, yeah. So, and or comprehensive climate models, I mean, by themselves fine, but without data, it's useless. No? And same with theory. So, and then remember what we did with the Sahara stuff. I mean, we started with comprehensive model that showed multiple equilibrium states. And then we fitted a conceptual model, a theory to these comprehensive ones. And then we used a model of intermediate complexity to show the transient. Now we're back to the comprehensive model, showing, well, it's not quite the case as the simple theories suggest, but it's more spatially inhomogeneous and so on. So I think there's no way out to use all three elements, no? Or maybe that's got you completely.
So yeah. I think there is a lot of interactions that I meant to illuminate with the different sites.
Yeah.
Maybe we don't always need all sites to be active in individual studies, but so I don't see it as a hopeless enterprise or as isolated disciplines, but they can play together. And I would say in case of North Africa, there was a lot of progress, and then maybe the simple conceptual model then is not the final answer, but still the theory, the dynamical systems approach and the methods, they can still help to answer the questions. And I think, yeah, that was what I wanted to stress in the end, the conclusions, that this model data integration that you just mentioned, that for a long time it has been difficult, especially linking complex ESMs with paleo records. I think there also is progress. So the models are faster, and also they can be more flexible. So there can be better integration.
I mean, we can now simulate a glacier cycle. No? It takes 2 years on the supercomputer, but we do it. and for the few thousand years, it's just a few months. Okay, now there's a new question, Denis. Denis, that's, I think, for you.
I think this is a we are reaching the end of this webinar. We
Yeah.
are just on time. So I would like to thank very much our two speakers for this very interesting talks, I think, from my point of view. And I hope that the audience was also very much interested. We had a lot of people attending this webinar. And again, I think it's a good start for this webinar series. We will reconvene by the end of July 23, with a new topic, high resolution paleoclimate data. So it should be again very interesting and stimulating. So I think that this celebration of 20th anniversary of climate of the past is in good way. So thank you again, and have a great time, and see you very soon.
Yeah.